This video will discuss some properties and some special kinds of matrices. Okay, so let's imagine we have some matrix here. So we take, if the number of columns is equal to the number of rows, each of those being n, then what we have is called an n by n square matrix, square being number of rows equal to the number of columns. So most of the time, or a lot of the time in computational chemistry, quantum mechanics, we're going to be working with matrices that are going to be square, and that makes a lot of things easier because you don't have to worry about, whether your number of elements are going to be compatible for multiplication or lots of other kinds of things. So one special kind of matrix that we're going to define is an identity matrix. In an identity matrix, the elements are going to be equal to 1 if you're on the diagonal, where elements are the row number and column number are equal, I equals j, and they're going to be 0 otherwise. So we could indicate this by what we defined earlier as the Kronecker delta, where where matrix Ij is equal to 1 if I and j are equal. It's equal to 0 if I and j are different. We might also indicate this by 1s going down a diagonal, and then these kind of bold-faced zeros on the outside, indicating that all of the off-diagonal elements on each side are 0, both in what we would call the upper triangle and the lower triangle. Okay, we can also define an inverse matrix. So if there's a matrix such that multiplying this matrix times a matrix A equals an identity matrix, and likewise A times this matrix will also give an identity matrix. So in the case that this is true, the matrix A to the minus 1 we would call an inverse matrix. So the inverse in general is fairly difficult to find, but for things like a 2 by 2 matrix, we can actually write down what the actual formula is for it. So in a 2 by 2, the inverse matrix is 1 over the determinant, A22, negative A12, negative A21, A11. We've exchanged the diagonal elements, and we have flipped the signs on the off-diagonal elements in addition to dividing by the determinant. Also of interest to us, if we take the inverse of a product of two matrices, that's equal to the inverses of each of those matrices but reversed. Okay, you should be able to convince yourself that if you take a look at this and substitute in b to the minus 1, a to the minus 1 here, next to a times b, the a to the minus 1 times a cancels and gives you an identity, and that leaves you with b to the minus 1 times b, which also gives you an identity. Okay, we have a property of matrices called the trace. The trace of A, which I'll often indicate in this type of notation, TR parentheses A, that's equal to a sum from I equals 1 to n of diagonal element AII. So the trace of an n by n square matrix is just a sum of its diagonal elements. So the trace of an identity matrix is just going to be the number of columns or rows n. The trace of a matrix which we'll define later to be Hermitian, the trace of a Hermitian matrix is equal to the sum of what we'll come to know as its eigenvalues. Mentioning these things now, just so you know later when we talk about Hermitian matrices, which are very, very important in quantum mechanics, that their trace is equal to the sum of their eigenvalues, just as in the previous video we saw that their determinant is equal to a product of their eigenvalues. Okay, and then we have the transpose of a matrix. So the transpose of our square matrix is just going to give us elements where we reverse the column and the row. So the diagonal elements stay the same, and the off-diagonal elements are traded with their partner on the other side of the diagonal. So AT I sub j, or sub ij, is equal to AJI. All right, we also have what it's called the adjoint, or sometimes called the Hermitian adjoint. I just call the adjoint of a matrix. That is, you take the transpose and then the complex conjugate of each of your elements. So the adjoint of a matrix is going to be flipping what side of the diagonal they're on, and then taking the complex conjugate of your individual elements. All right, and then we would say if a matrix equals its transpose, you have what's called a symmetric matrix. So we have, and that's assuming that all of our elements there are real as well. So in that case, we have equal values on either side of the diagonal. So that gives us a symmetry about the diagonal, symmetric matrix. Alternatively, if a matrix equals its own adjoint, then that's what we define as being Hermitian. So there, in general, our elements can be complex, though they could also be real. Any Hermitian matrix that is real is also symmetric. So in general, we have that the elements on the other side of the diagonal have the same real part, and they have the opposite imaginary part. Okay, then we can define if a matrix's transpose is equal to its inverse, then what we have is called an orthogonal matrix, assuming that all of your elements are real. And if your matrix's adjoint is equal to its inverse, then you have what is called a unitary matrix, and there your elements could be complex. It doesn't make a lot of sense at the moment why unitary matrices are important, or why we would even take note of this, but this will come up down the line in a couple of videos, because unitary matrices and Hermitian matrices are extremely important in computational chemistry. All right, so one property then of unitary matrices, since their adjoint is their inverse, is that the adjoint times itself will give you an identity matrix, because that is the definition of inverse. So, and also the magnitude, or the determinant of a unitary matrix, as listed in the previous video, is going to be equal to 1. And all of the eigenvalues of a unitary matrix, as we'll discuss in future videos, are equal to 1 as well. So an example in 2x2, an example of all possible unitary matrices or I guess I should say all possible orthogonal matrices in 2 dimensions, would be equal to this, where our elements are cosine theta down the diagonal, and then sine and negative sine theta there. Because if you take the transpose of this matrix and multiply it times itself, you'll find that the elements you get are equal to an identity matrix in 2x2, where these angles are any value of theta, which is some real number. So those are some properties of matrices which we'll make extensive use of in the rest of this chapter and in further chapters on computational chemistry.